Welcome to all. Today we will discuss what is the invariant direct sum. Okay, suppose V is equal to direct sum of W1, W2 up to Wk, where all these Wi's are subspace of V. Suppose V is equal to direct sum of W1 plus W2 up to Wk, and Wi is invariant under some given linear operator T. Okay, Wi is invariant under some given linear operator T. For such a decomposition of V, T induces a linear operator T1, T2 up to Tk on W1, W2 up to Wk respectively. Okay. T induces a linear operator T1, T2 up to Tk on these subspaces W1, W2 up to Wk respectively. Okay. That is, if alpha belongs to V is any given vector, alpha is a any vector from a given vector space, then alpha can be written as uniquely expressed as alpha is equal to alpha 1 plus alpha 2 up to alpha k by the definition of direct sum. Okay, where alpha I belongs to Wi. Then applying t on both sides, t of alpha is equal to t of alpha 1 plus alpha 2 plus up to alpha k. Okay, then t of alpha is equal to t of alpha 1 plus t of alpha 2 plus up to t of alpha k. Okay, now look at this. This t of alpha 1 belongs to w1, alpha 2 belongs to w2, alpha k belongs to wk. But W1 is invariant under T. W1 is invariant under T. Hence, this T of alpha 1 belongs to W1. Hence, we can say that instead of T, we can write T of W1 of alpha 1. This T of alpha 2 belongs to W2. Okay. Hence, we can write this T like T of W2 of alpha 2 up to so on. This T of alpha k belongs to Wk, since Wk is invariant under T. Instead of T, we can write T of Wk because this element belongs from Wk. T of Wk of alpha k. Okay. Next. Okay. This is the T induces a linear operator T of W1, T of W2 of T of Wk. Okay. This is the definition of invariant direct sum. Here all Wi are invariant under T. Okay. The definition is same as like direct sum because and here the invariant words come. Okay. Why? Because all these subspaces are invariant under T. Okay. Now next theorem is theorem. Let T be a linear operator on finite dimension vector space V over F. F is the field. If T is diagonalizable, if T is diagonalizable, and if C1, C2, C3 up to Ck, all these are distinct characteristic values of T. Okay, are distinct characteristic values of T. Then there exists a K linear operator such that E1, E2 up to Ek on V, on vector space V, such that first condition. Okay, the Yesterday theorem is different, and the today's theorem is also different from each other. Okay, t is equal to c1 into e1 plus c2 into e2 plus up to ck into ek. Okay, and second condition, I is equal to e1 plus e2 plus up to ek. Okay, and third condition, ei into ej is equal to 0 where I is not equal to j, where I is not equal to j. And fourth condition, each ei is projection on v. Each ei is a projection on v where I running from 1 to k, and that is ei square is equal to ei. And range of ei is characteristic space for t associated with ci. Range of ei is nothing but characteristic space for t associated with ci. These condition, two, second, third, fourth, and fifth. These are the condition. It's same. It's same. But here the one more condition is added. Okay. What is that condition? T is C1, E1, C2, E2 plus up to CK, EK. 2 to 5 is the same condition as we seen in previous theorem. Okay. Now conversely, hmm? If conversely, if there exist k distinct scalars, okay, if there exist k distinct scalar c1 c2 up to ck and k non-zero linear operator e1 e2 up to ek which satisfies the condition 1 2 3, then t is diagonalizable. Okay, c1 c2 ck are eigenvalues, that is characteristic values, and k is be a non-zero linear operator, and e1 e2 up to ek which satisfies condition 1 to 3, then t is diagonalizable. We have to prove t is diagonalizable. And and c1 c2 up to ck are the characteristics values of t, and the condition 4 and 5 also satisfy. If these ci's are characteristic values, then condition 4 and 5 also you have to prove these 4 and 5 also satisfy. Okay, understood the theorem? Once again, look at the theorem. This condition is new. Okay, we seen these four condition in previous theorem. Okay, first we assume that t is the diagonalizable and these are the distinct characteristic value. Then after then look the statement, there exist k linear operators. Okay, we have to prove the existence of these k operators such that these five conditions holds. And after that, conversely, assuming if there exist k distinct scalar ci's such that k non zero linear operator ei e1 e2 up to ek which satisfies the given condition 1 2 3, assuming these three condition holds, then we have to prove t is diagonalizable conversely. Okay, and also if condition 4 and 5 holds, we have to prove, yeah, we have to prove these c1 c2 ck are characteristic values of t, then condition 4 and 5 also satisfy conversely. Okay, the proof of the theorem. Okay, suppose suppose a linear operator t defined on finite dimension vector space v. Okay, this t is diagonalizable, assuming t is diagonalizable, and c1 c2 up to ck are distinct characteristic values of t, assuming this statement. Okay, now again, let w1 w2 up to wk be the characteristic spaces associated with characteristic values c1 c2 up to ck respectively. Okay, but we know that t is diagonalizable if and only if V is direct sum of characteristic spaces of T. In the definition of direct sum, we seen the three remarks. Okay, by that remarks, T is diagonalizable if and only if V is direct sum of characteristic spaces of T. Okay, here T is diagonalizable given we are assuming that T is diagonalizable and Wi are the characteristic spaces. Therefore, we have to prove that. Therefore, sorry, we have W is equal to V is equal to W1 plus W2 plus up to WK. Okay, we can write V is the direct sum of W1, W2 up to WK. Okay. Now condition 2, 3, 4, 5 are true obviously. Why? By previous theorem. We seen in the previous theorem. In previous video, this second, third, fourth, five other condition are true obviously by previous theorem. We have to prove only the first condition, which is T is equal to C1 E1 C2 E2 CK EK. Okay, the sum of C1 E1 plus C2 E2 up to CK. We have to prove only this condition. By previous theorem, these all the fourth condition, second, third, fourth, and fifth are true. Okay. Next, by previous theorem. Now we have to prove the only first condition. Okay, that is to prove that there exist k linear operators E1, E2 up to Ek on V. Okay, such that T is equal to C1 E1, C2 E2 up to Ck Ek. Okay. For this, assume let alpha belongs to V be any vector. Okay, alpha belongs to V be any vector. And we have I is equal to by first condition. Okay, by previous theorem, I is equal to E1, E2 up to Ek. Apply this operator on alpha. Okay, I of alpha is equal to E1 plus E2 plus up to Ek of alpha. Okay, then alpha is equal to I of alpha is equal to alpha because I is identity operator and operate this alpha on each operator E1 of alpha plus E2 of alpha plus up to Ek of alpha. Okay, which is equal to alpha is equal to running this I from 1 to k summation I is equal to 1 to k ei of alpha. This equation we can write like in the summation form. Give it as equation number 1. Okay. Now again operate t on both sides. Okay. Operating t on both sides, t of alpha is equal to t of summation I is equal to 1 to alpha k ei of alpha. But t is linear. Hence this t can write in summation. Okay, t of alpha is equal to summation I is equal to 1 to k t into t of ei of alpha. Equation number 2. Give it as equation number 2. Why we can write like this? Because t is linear. By the definition of linearity, we can write like this. Okay. Since Wi is the range of ei, we know that Wi is the range of ei. Okay. Ei of alpha belongs to Wi by the statement number 5. Wi is the range of ei. Okay. Hence, ei of alpha belongs to Wi. I is equal to 1 to k. Also, the Wi is the characteristic space associated with characteristic value Ci. Okay. Wi is the characteristic space. Okay. With associated with characteristic value Ci. Okay. Hence, T of Ei of alpha is equal to Ei of Ci into Ei of alpha for I is equal to 1, 2 up to k by definition. How we can write like this? Okay, how we can write like this? Because Ci is the eigenvalue and Ei of alpha belongs to this Ei of alpha belongs to Wi, but Wi is characteristic space. Hence, each vector in Wi is the eigenvector. Okay, that is characteristic vector associated with the Ci. Hence, we like by the definition by the definition of eigenvalue eigenvector T of Ei of alpha is equal to Ci into Ei of alpha. Give it as equation number 3. Using 3 in equation number 2. This equation in 2. T of alpha is equal to equation 2 becomes T of alpha becomes summation I is equal to 1 to k Ci into Ei. Okay. Instead of T of Ei of alpha, we can write Ci into Ei of alpha. Okay. Hence, running summation from I is equal to 1 to k. T of alpha is equal to C1 E1 of alpha, C2 E2 of alpha up to Ck Ek of alpha. Hence, Ti of alpha is equal to C1 E1 plus C2 E2 plus up to Ck Ek of alpha for all alpha belongs to V. Why? Because alpha is any vector from V. Okay. Therefore, T is equal to C1 E1 plus C2 E2 up to Ck Ek. Hence, the first statement holds. Okay. And the statement number 2, 3, 4, 5 are obviously true by previous theorem. Okay. Now we have to prove converse. Okay. Conversely, assume that C1, C2, Ck are distinct scalar, not eigenvalues. We have to prove that are the these are the eigenvalues. Okay. We have to prove this. Assume that these Ci are distinct scalar and E1, E2 up to K are K non-zero linear operator on V such that these conditions first, second, third conditions are obviously true and we have to prove that T is diagonalizable and C1, C2 up to Ck are distinct characteristic values of T by the theorem by the given theorem in the given theorem we have to assume that these three statements are holds and e1 e2 are all are k non-zero linear operator and we have to prove that t is diagonalizable and c1 c2 up to ck are distinct characteristic values of t and also c ei square is equal to ei. That is, each ei is projection on V. Okay, for I is equal to 1 to k. And we have to prove D. The range of ei is characteristic space corresponding to characteristic value Ci. Okay, we have to assuming these three statements are correct. We have to prove these four are correct. Okay, we have to prove these four statement, huh, corresponding to the characteristic value C. First, you have to prove statement number C. Statement C. Okay, what is EI square is equal to EI? That is, each EI is projection on V. Let for this, let alpha belongs to V. Be any vector. Let alpha belongs to V be any vector and we have I is equal to E1 plus E2 plus up to EK here. Statement number 2, assuming statement number 2. Then operate this operator on alpha. I of alpha is equal to E1 plus E2 plus up to EK of alpha, which implies I of alpha is equal to alpha and apply this alpha on each EI. each e1 of alpha plus e2 of alpha up to ek of alpha. Okay, again operating again ei for I is equal to 1 to k on both sides. This becomes ei of alpha, which is equal to ei of e1 plus e1 alpha plus e2 alpha up to ek alpha. Okay, which implies ei of alpha is equal to ei into e1, ei into e2 up to in between some in between this equation ei is present. Okay, in between some equation in between this e2 to ek, the ei is also present in ei of alpha into ei of alpha plus up to ei of alpha, ei into ek of alpha. Okay, in between these ei is present somewhere. Okay, so ei of alpha is equal to ei into e1 0, ei into e2 0, ei into ei is square of alpha, and all these terms are negative. Why? Because given there ei into ej is 0 for I is not equal to j, but I equal to j is e square. Okay, so ei of alpha is equal to ei square of alpha. Hence, ei square is equal to ei for all alpha belongs to V, and ei square is equal to, that implies ei square is equal to ei for all I is equal to 1 to k. Hence, each ei is projection on V. Okay. Next, to prove that, C1, C2, Ck are characteristic values. Okay, these are the characteristics value. We have to prove this. Okay, for this, let alpha belongs to V be any vector, and operating T on ei of alpha, we get T of ei of alpha summation j running from 1 to k cj into ej of ei of alpha. Okay, T of ei of alpha, this ei of alpha and this of this ei of alpha. Hmm? Instead of t we can write like j running from 1 to k cj into ej instead of this t. Why? Because t is equal to c1 e1 plus c2 e2 plus up to ck ek. Hence we can write like this: t of ei of alpha is equal to summation j is equal to 1 to k cj into ej into ei of alpha. Okay, next, that is t of ei of alpha is equal to summation j is equal to 1 to k cj into, by associativity na, ei into ej into ei of alpha, which implies ci is equal to, run this j from 1 to k. Okay, then all the ei into ej is equal to 0 for all, for I not equal to j, running these terms from j equal to 1 to k, then this becomes ci, and ci into ci, ei into ei square of alpha, and all the terms are 0. Instead all the terms are 0 for I not equal to j. Hence, T of ei of alpha is equal to Ci into ei of alpha, because each ei is projection on V. Okay. Hence, we can write like this: ei square is equal to ei for all ei of alpha. Hence, by the definition of uh, characteristic vector, Ci is the characteristic vector. Since why? Since ei is not equal to 0. These all the linear operators are non-zero for I is equal to 1 to k. then there exists at least one non-zero vector beta belongs to V such that EI of beta is not equal to 0. Otherwise, all EIs are 0 operator. Okay, hence from 1 T of EI of beta is equal to from 1 T of EI of beta is equal to Ci into EI of beta. This is the eigenvector, this is the eigenvalue, this is the any vector alpha. Any vector belongs to Wi. Okay, why Wi? Because Wi is the range of Ei, huh? For I is equal to 1 to up to k, and Ei of beta is not equal to 0. Why? Because any characteristic vector is non-zero vector. Okay, this shows that all these Ci's C1, C2 up to Ck are the distinct characteristic values of T. Okay. Now, to prove that C1, C2, Ck are the only characteristic value of T, okay, uniqueness, that is uniqueness of Ci. All these are the only. Apart from this, there does not exist any other characteristic values. Okay, we have to prove that C1, C2 up to Ck are the only characteristic value of T. Let C be the any other characteristic value. To prove this, we have to assume another C apart from this. Let C be any other characteristic value of T such that C is not equal to Ci for I is equal to 1 to k. That is C minus Ci is not equal to 0. Taking Ci to left side for all I. Okay. Then there exists a non-zero vector alpha belongs to V such that T of alpha is equal to C alpha. Okay, we have assumed C is any other characteristic value by alpha. By the definition of characteristic vector, T of alpha is equal to C of alpha, which is not equal to 0. Characteristic vector are always non-zero. Okay, so it implies T of alpha is equal to C1 E1 of alpha, C2 E2 of alpha up to Ck Ek of alpha, which is not equal to 0. This C of alpha can written like this by the definition in the given statement number 1. Okay, now this T can written like this. Okay, this that implies summation I is equal to 1 to k Ci into Ei of alpha. Okay, Ci into Ei of alpha, which is equal to this term like that is this term like this, and I of alpha, is it alpha is nothing but I of alpha, and I of alpha is written like this. C is, as it is, I means E1 plus E2 plus up to Ek na. So C is a common term. C into E1 of alpha, C into E2 of alpha, C into Ek of alpha. Here's the reason. T is equal to Ci into Ei. Okay, for I equal to 1 to k. This T becomes like this, and this alpha becomes I of alpha, which implies C into E1. Okay, here the reason. I is equal to 1 to k, summation 1 to k Ei. Hence, this summation I is equal to 1 to k Ci into Ei of alpha is equal to summation. C is the common. Then I is equal to 1 to k Ei of alpha. Okay. Again, that implies taking this to the right side, left side, I is equal to 1 to k Ci minus C into Ei of alpha, which is equal to 0. Give it as equation number 3. If all the Ei's are 0, then we get contradiction. Okay, we get contradiction to 2. Where is the contradiction to E here? If all the Ei's are 0, then it becomes 0. But here the T of alpha is not equal to 0. Hence, all the EIs are not 0. If all the EIs are 0, then we get contradiction to 2. Then we must have EI of alpha is not equal to 0 for some I. Okay. Hence, with respect to this particular I, operate EI on both sides of 3. Operate EI on both sides of E. Apply EI on this equation. Okay. EI of summation j running from 1 to k Cj minus C of Ej of alpha. Okay. Which is equal to EI of 0. EI of 0. 0 maps to 0. Under linearity, 0 maps to 0. Na? Okay. And j is equal to 1 to k Cj minus C and Ei into Ej. Why? Because Ei is the linear operator. Okay. Here j running from 1 to k and Ei is linear operator. Hence, we can write in the bracket. Hence, Ci minus C is equal to Ei square. Run j from 1 to k. Run this j from 1 to k. This become Ei into Ei is Ei square of alpha and all the other terms except I. Ei into Ej is equal to 0 for I is not equal to j. By using this condition, after running these terms j from 1 to k, we get Ci minus C into Ei square of alpha is equal to 0. Okay, hence, but Ei is the projection on V. Hence, Ei square is equal to Ei. Hence, Ci minus C into Ei of alpha is equal to 0. Okay, but Ci minus C is not equal to 0. Why? Because this C and these all the Ci's from 1 to k are different characteristic vectors is equal to 0. But the product of these two terms is 0. Hence, it implies Ei of alpha is equal to 0. Here we get which is not true. Why? Because we assume that Ei of alpha is not equal to 0, which is not true because Ci minus C is not equal to 0 and Ei of alpha is not equal to 0. The product of two non-zero terms becomes 0 here, we get. Hence, this shows that there does not exist any other characteristic values except C1, C2 up to Ck. We get the contradiction. Okay, now we get the contradiction. Hence, there does not exist any other C except these Ci's. Okay. Now we have to prove statement number A. Statement A. To prove that T is diagonalizable. Okay, T is diagonalizable. If it is sufficient to prove that the vector space V is spanned by all the characteristic vector of T. Okay, it is sufficient to prove that all the characteristic, all the vectors of T, all the, it is sufficient to prove that the vector space V is spanned by all the characteristic vectors of T. Then T must be a diagonalizable. Any vector alpha belongs to V is spanned by characteristic vectors of alpha. Okay, from 1 we can write by previous statement from 1, equation number 1, we can write like T of Ei of alpha is equal to Ci of alpha. Okay, Ci are the characteristic vector where I running from 1 to k. Okay, for each alpha, each Ei of alpha belongs to range of Ei. Okay, okay, this Ei of alpha belongs to Wi and this is the characteristic vector, eigenvector. Okay, this implies that any non-zero element of range of Ei is characteristic vector of T with respect to Ci. Okay, this implies that any non-zero element of range of Ai is characteristic vector of T with respect to Ci. Okay, this ei of alpha belongs to wi, and this is the characteristic vector. Hence, let any alpha belongs to V be any vector. Let alpha belongs to V be any vector. We have I is equal to capital I, identity operator. I is equal to small I 1 to k summation I is equal to 1 to k ei. I is equal to e1 plus e2 up to ek. Na? And operate this operator on alpha. So, I of alpha is equal to e1 plus e2 up to ek of alpha. Hence, alpha I of alpha is equal to alpha and e1 of alpha plus e2 of alpha up to ek of alpha. This shows that every alpha belongs to V can expressed as linear combination of characteristic vector. Okay, this E1 of alpha belongs to W1. This is belongs to W2. This is belongs to WK. Okay, this shows that every alpha can be expressed as linear combination of characteristic vector. But W1, W2, W3 are the characteristic spaces spanned by characteristic vector. Okay, that is the vector space V is spanned by characteristic vector of T. Hence, T is diagonalizable. This is the proof of T is diagonalizable. Okay. Now, statement D. Let Wi be the characteristic space associated with characteristic value Ci. To prove that range of Ei is Wi, we have to prove the range of Ei is W. That is, range R of Ei is equal to Wi for all I. Okay. Now, beta belongs to range of Ei, which implies beta is equal to Ei of alpha for some alpha belongs to V. This is the definition of range of Ei. Okay. If beta belongs to range of Ei, implied beta is equal to Ei of alpha. Operate T on both sides. T of beta is equal to T of Ei of alpha. T of beta is equal to T of Ei of alpha means Ci into Ei of alpha, because Ei is the eigen vector, characteristic vector. Okay. Hmm? So T of beta is equal to Ci into Ei of alpha, which implies T of beta is equal to Ci of Ei of alpha means again beta. Okay, which implies beta is the characteristic vector of T. This beta is the characteristic vector of T with respect to Ci. It implies beta belongs to Wi. Okay, beta belongs to Wi. This implies 0 not equal to beta, which belongs to range of Ei, implied beta belongs to Wi. Hence, range of Ei is characteristic space Wi of T with respect to characteristic value Ci for I is equal to 1, 2 up to k. Therefore, range of Ei is equal to Wi. Okay, so today we prove the theorem, all the statement, all the statement of theorem. Okay, in the next lecture we will see again one more theorem is there. Okay, thank you.